Here's the solution to question 1 from the Physics 211 practice exam. So here we are thinking about a stone falling into a pool of water. It falls when it's above the surface and floats when it's beneath. So here I'm just going to draw a schematic of what we expect. Height above the water here, time here. Now, I've got another version of this graph over on the right side of my board that I will make precise, but here we're just sort of predicting what will happen. So here's the surface of the water. And we expect the stone to accelerate downward when it's in the air, but then we know it accelerates upward while it's beneath the water. We don't know yet, of course, what the numerical values are. We will find them. But what we know is, in this part, in the first stage, the acceleration is, we're told it's minus g downward, and the problem gives you a hint to use 10 meters per second squared to make the numbers come out nicely. In the second stage of the motion, here, we know the acceleration is plus 5 meters per second squared. Now, in this question, you can do this primarily using graphs to figure things out. You can primarily do this with equations. I'm going to use something of a hybrid method here. So the first thing I will find is how much time this takes. So the time to hit the surface. So in the first stage, I know the height as a function of time is minus 1/2 gt squared plus h. We set that equal to 0 to find when it hits the surface of the water. Solving for time, let's see, so we've got 1/2 gt squared equals h. So t equals the square root of 2h over g. So what is this? Well, h is 5 meters, so this is the square root of 10 meters over 10 meters per second squared, which is 1 second. That's really nice. This means we hit the water after 1 second. So now let's move over to our graphs and graph what happens here. So that means for 1 second, the acceleration is minus 10. What's the velocity do in that 1 second? Well, in 1 second, if the velocity is changing at 10 meters per second downwards, it would wind up here. So we can draw that part out. And the position, well, we know, we've just calculated that we're starting at a height of 5 meters here. H equals 5 meters, and sinking down to the surface. In a concave down parabola with decreasing slope. Now, we can, here I want to take the other approach, or illustrate the other approach, that the area between the velocity graph and the time axis is the distance traveled. So what is this area? Well, this is a triangle with a width of 1 second, a height of 10 meters per second. So this is, here, 5 meters, minus 5 meters that we've gone down. Now, we have to rise back to the surface, right? But we know that the slope rising back to the surface is only half as much, right? An acceleration of plus 5 meters per second squared. So that means that my velocity versus time graph on the way back up only goes half as fast. So now that means it's going to take 2 seconds to get back to 0. Now, here I'm going to do everything else with my graphs. this is another triangle here, right? So the area of that triangle, actually I'm going to put the areas inside the triangles. It will be easier to read that way. Pardon my mess. So this is an area of minus 5 meters. So we've gone 5 meters downward while falling. Now, what's going on in this second stage? Well, we are still sinking downward in the pond, but our velocity is getting less and less negative. The buoyant force is bringing us back up. But this area, let's see, we've got 2 seconds times 10 meters per second. This area is minus 10 meters. So what that means is that during this part of the motion, it takes 2 seconds of time and 10 meters of movement to bring us to a rest. During this period, our acceleration is plus 5 meters per second. Now, we then need to come back to the surface. We're 10 meters below the water. So in order to get back to the surface, I need 10 meters of positive displacement. Right? I can expect this to be symmetric. I'm going to switch colors here. I can expect this to be symmetric. So I would reach the surface here. My acceleration is the slope of my velocity curve. And my acceleration doesn't change, right? It's still plus 5 meters per second. So I'm now drawing a triangle with an area of plus 10. Notice this triangle has the same area as this one, plus 10 meters. Base is 2 seconds. Height is 10 meters per second, area is 10 meters. And this is really all there is to do in this problem. I've done everything. What's the interpretation here, right? So let me many of you may be shocked that I figured everything out without really writing any more equations. So let's highlight what some of these moments are. This moment is when it hits the water. This moment is when it reaches its lowest point. Notice that this is the point where the velocity is 0. Lowest point. And this moment, again, is where it rises to the surface. Reaches surface. So I have, and the slope of the velocity is the acceleration, right? So this slope is minus 10. I've gone down 10 meters per second in 1 second. And then this slope is plus 5. My velocity is increasing by 5 meters per second every second. So after 1 second of floating, I am here. This is my deepest point, so the position is flat, the deepest point where the velocity is 0. And then after 1 second, my velocity is plus 5. After 2 seconds, my velocity is plus 10. And this area of 10 meters is enough to get me back to the surface. So I've answered all of the other questions, all of the other parts of this. I'm putting my chalk down and picking up what the questions are. Part B asks for the maximum depth. Well, it's 10 meters. Part C asks what the total amount of time is between when the ball is dropped and when it reaches the surface. 5 seconds. And part D is sort of how we did all the other parts, right? The total amount of time interpreting these areas. This is the distance that the ball travels as it is falling in this part, from 5 meters to 0. This is the further distance below the surface that the ball travels while buoyancy is bringing it to rest. So still going downward. And then this is the distance that we travel on the way back up. So part D says, can you do B and C by graphical means alone without writing any algebra? Yes, we can. This is the simplest way I find to do this problem. But some of you may be asking for me to do it with equations as well. So what I'm going to do now is I'm going to erase the left-hand side of my board and show you another approach that uses equations to arrive at these same things. So, yes, we're good. Stage 1, time to hit surface. I already did this one, I'm just recopying it. So, y of t is h minus 1/2 gt squared. So we set this to 0 to find when it hits the surface. 0 equals h minus 1/2 gt squared. We saw earlier that t is square root 2h over g, which is 1 second. Then the velocity when it hits the water is going to be v naught minus gt, but v naught 0 here because it's dropped from rest. So this is going to be minus gt, or minus 10 meters per second. Hey, we figured this out graphically over there. Now in stage 2, when it's floating, and I'm going to color code this here. I'm going to use blue again because that's the color I used in the graphs. Stage 2, floating up. Here, y of t is, well, let's write down everything. 1/2 at squared plus v naught t plus y naught. Now many of these things are 0. This is 0 because we're starting from ground level, and this velocity is the velocity with which it hits the water. So what are the things, I can also write down the velocity equation here. V of t is, v naught's 0, so just, no, v naught's not 0. What am I saying? V naught plus at. So these two things describe both the blue curve and the yellow curve there. So let's figure out how deep it goes. So the deepest point is when v of t equals 0. So we set this to 0. 0 equals v naught plus at. Now we can solve this. I want to subscript this to make clear what's going on. T deepest I'll use the next one. T deepest is minus v naught over a, which is minus v naught is 10 meters per second over 5 meters per second squared equals 2 seconds. So this is how much time it takes to go from the point where it hits the water to the deepest point. So we've now learned that this is 2 seconds from what we just did. Now let's figure out the deepest point. So So the position there, x of t equals, right, or y of t, doesn't matter what symbol you use in one dimension. I just plug into this formula, 1/2 at squared plus v naught t equals, let's see, a is plus 5, t is 2, so I've got 1/2 5 meters per second squared times 2 seconds squared plus negative 10 meters per second times 2 seconds. I know I'm being anal about my units. Let's see. 2 squared is 4, 1/2 is 2, times 5 is, did I do this right? 10. So this is plus 10. This is minus 20. So this gives me minus 10 meters. So minus 10 meters is the deepest point. That's what I just found, right? The deepest point is 10 meters below. Now, how much time does it take to rise to the surface? Well, I'm going to erase this because I'm out of room. So I'll give you all a minute to look at it. You can pause the YouTube video if you want. That's just part B that I have done. And now let's do part C. So it reaches the surface when y equals 0. So we've got our y of t equation. Y of t equals 1/2 at squared plus v naught t. I can set this to 0. Cancel out a factor of t from both. That tells me t equals, let's see, I have a factor of 2. So this is 2 v naught over a with a minus sign. Yep. So that is 4 seconds. Because v naught is minus 10 meters per second here, a is plus 5 meters per second squared. So this tells me that this amount of time is 4 seconds, which is what I did earlier. So I did all of this sort of spewing equations at you on the left-hand side of the board, but really all I did was use algebra to catch up to the same things that I did geometrically here. I find the geometric interpretation here to be much more elegant, because it tells you exactly what is happening in each stage of the motion. So this is problem 1 on the practice exam.